Welcome to Physics Lesson 8.5. Simple machines. Yeah. Alright, so we talked about work, we talked about energy, we talked about power, but let's talk about how machines make our lives easier. Alright, so the whole thing of a machine is they have this thing called mechanical advantage. And basically what that is, it's a ratio of how much force you have to put in and how much force the machine that you're using puts out. So our mechanical advantage is our output force divided by our input force. So formula-wise, MA is our mechanical advantage. This would be our resistance force, so we'll call that resistance, and this would be our effort force or our input force. Okay, so machines can increase force, but they cannot change the amount of energy, right? So that goes back to that whole conservation of energy. So an ideal machine is going to transfer all of its energy to output, right? So input should equal the output work, right? And work is our measure of that energy. The problem is machines aren't efficient. So we're going to have to take another ratio. And the way that we can take this is our input distance versus our output distance. And that's going to be our ideal mechanical advantage. So the closer that is to 1, the better. Alright, so how efficient a machine is, we do that on percents. So basically our efficiency can either be looked at as a work output over input ratio times 100, or we can look at our mechanical advantage over our ideal mechanical advantage. Either way, that's going to give us a percent for our efficiency. So the higher the efficiency number, the better the machine is. The better the machine is transferring the amount of energy to whatever object you're trying to do, or whatever the machine's supposed to do. Alright, so let's go ahead and give that a try. So let's say for some reason you're trying to lift a really big rock using a lever. We are putting in an effort force, so our force input should equal 225 newtons. And our output is 1,250 newtons. Holy cow, that's a big rock. And we're trying to do this we're going to lift this a distance of 0.3 meters. So we'll call this delta y because if I'm picturing this as, this is a rock, and this is our lever, and we have some kind of fulcrum right here. I'm picturing the rock going up a distance of 0.13 meters. That's why I have the delta y there. Okay, so efficiency-wise, not horribly inefficient, 88.7%. How far did you have to move the other end of the lever? So how far did you have to push that in order to get it to raise that much? So we have to break this up into a couple things. The first thing we want to do is we want to figure out our work output. So our work output, I'll change colors here, should be our force output multiplied by the distance that we are going or applying that force to. And that should equal 162.5 joules. The next thing we need to figure out is how much work we are putting in. Right? So we can use our efficiency formula, which looks like this. Work out over work in times 100 to figure that out, since we were given the efficiency. So our efficiency is 88.7%. And that equals our work out, which we now have, 162.5, divided by how much work we're going to put in, times 100. All right, first thing we can do is get rid of this, 100. That's going to get rid of our percents. So that'll cancel out that, cancel out that. We will have 0.887 equals 162.5 over the amount of work we're going to put in. So the first thing we want to do is make sure that we get this variable out of the denominator. We do not want that in the bottom. So the first thing we got to do is multiply each side by this variable to get rid of it. So now we have 0.887 multiplied by the work input equals 162.5. Now we can divide by this 0.887 on each side. And that should give us a work input of 183.2 joules. All right, so that's how much work we're putting in. So then, one last step here. This work in should again equal our force times our distance. So 183.2 equals the effort force that we are putting in. So this is 225 times 5, and then our delta y should be 0.81 meters. All right, good times. Go back up here, check our answer, make sure I didn't miss anything. Yay! Ooh, that should be a lowercase m, not an uppercase m. It's not a mega. It should be a meter, which is lowercase. Ooh, error. Okay, anyways, I will talk to you another time. Thank you for stopping in, and goodbye!